In this lesson, we'll be looking at Kepler's laws of planetary motion. We're going to look at the shape of a planet's orbit. We'll find out where the sun is located in the orbit relative to the planet. We'll find out if planets move at the same speed throughout their orbits or if they change speed. And then we'll see how the time a planet takes to orbit is related to its distance away from the sun. All of these things are going to be put together with three laws that describe planetary movement. You might think that the planets move in circular orbits with the sun at the center of the orbit. In fact, that's what people thought for many, many years. The astronomer Johannes Kepler discovered that the planets actually move in elliptical orbits. An ellipse is like an elongated circle, and instead of having one center, an ellipse has two focal points, or foci. The foci of an ellipse define what its shape is, sort of like the center of a circle defines the circle. In an elliptical orbit, the sun is located at one of the foci of the ellipse. Usually, there's nothing at all at the other focal point of the ellipse. This is the first one of Kepler's three laws of planetary motion. Planets move in elliptical orbits, with the sun located at one of the ellipse's foci. Planets speed up and slow down as they move through their orbits. They move fastest when they're close to the sun, and when they're farther from the sun, they move much slower. The reason for the change in speed is just gravity. Imagine a planet that's starting to come back towards the sun from the far end of its orbit. Gravity from the sun is going to be pulling the planet forward, making it accelerate faster and faster. By the time it gets close to the sun, it's going to be moving. As the planet moves away from the sun, gravity is going to start pulling it backwards. As the planet moves farther away, it's going to be going slower and slower because of that backward drag from gravitational force. When the planet reaches its farthest point away from the sun, it will be going its slowest. Once it passes that point, it'll start speeding up as it feels the pull of gravity from the sun pulling it forward. The way the planet's speed changes is very predictable. If we imagine a planet that orbits around the sun in 14 hours, and we map out where it is each hour, in the first hour, it goes from its farthest point away from the sun just a little bit farther because it's not going very fast. If we draw an imaginary line from the planet to the center of the sun, we can see that at the beginning and the end of that first hour, those lines make kind of a triangular shape. We'll label that area A to keep track of it. Now, a little bit later on, the planet's moved over here 6 hours later, and in the next hour, it's going much, much faster, and it moves all the way over here. The imaginary line between the planet and the sun now is making a different shaped triangle. We'll call that one B. It turns out that A and B both have exactly the same area. In fact, any of the other triangles that we could draw as the planet moves the same amount of time but a different distance, they all have the same area. A is the same area as this one, or B, or this one over here. As long as the amount of time is the same, the area swept out by that imaginary line is equal. In fact, that's Kepler's second law. An imaginary line between a planet and the sun will sweep out equal areas of the orbit in equal times. And what all of that means is that planets move faster when they're close to the sun and slower when they're farther away from the sun. Now let's look at how long it takes a planet to make an orbit and how big the orbit is. It seems pretty obvious that if a planet is making a smaller orbit, it's going to do it faster than if it's making a larger orbit. The large orbit's going to take longer to complete. Kepler defined this relationship between the time for the orbit and the size of the orbit in his third law, which says that the square of a planet's orbital period is proportional to the cube of the planet's average distance from the sun. Kepler's third law is easier to understand in its equation form. The square of the planet's orbital period is in the equation as t squared. And that's proportional to the cube of the planet's average distance from the sun. which we call a cubed in the equation. The t in the equation represents the orbital period of the planet, which is the time that it takes for the planet to complete an orbit, and we measure that in Earth years. Earth's orbital period is 1 year. The average distance of the planet from the Sun as it goes through its orbit is measured in a unit called an astronomical unit. Astronomical unit is defined as the average distance from the Earth to the Sun during Earth's orbit. This is a handy unit for measuring distances within the solar system. So Earth's orbit is an average of 1 astronomical unit, or 1 AU, away from the Sun. Let's look at an example problem. According to Kepler's third law, how long will a planet take to orbit the Sun? Remember, the orbital period is capital T if its average distance from the Sun, which, remember, the symbol for that is a lowercase a for average distance, is 9 astronomical units. As always, we're going to use the Q's system to solve this problem. Your knowns are the values you know from the problem. The unknown is what you're trying to find. You need to know what equation you're going to use so you can substitute the values into the equation and then show each step as you solve. This problem only has one known value. It tells us that the average distance of the planet from the Sun is 9 astronomical units. So our known is A equals 9 AU. Our unknown is the orbital period, because the question asks us how long the planet will take to orbit. So T, the orbital period, is our unknown. It's no surprise that we're going to use the Kepler's third law equation to solve this. T squared equals A cubed. The next step is to take our known, the 9 astronomical unit distance, and substitute it into the equation. So T squared equals 9 cubed. You might notice that we're not using the units in the calculation like we normally do. Because the astronomical unit is an arbitrary unit, it doesn't necessarily transfer into the equation. We use our calculator and cube the 9 cubed, which is 9 times 9 times 9, equals 729. So T squared is 729. But the answer we're looking for is T, not T squared, so we're going to take the square root of both sides of the equation. The square root of 729 is 27, so T, the orbital period of the planet, is 27 Earth years. If the planet is orbiting the Sun 9 times as far away as Earth is from the Sun, it will take 27 Earth years to make its way around. In this lesson, we looked at Kepler's first law, which says that planets move in elliptical orbits, and that the Sun is located at one of the ellipse's foci. We looked at Kepler's second law, which says that an imaginary line between a planet and the Sun will sweep out equal areas of the orbit in equal times, which really just means that planets speed up when they come closer to the Sun and they slow down as they move farther away from the Sun. Finally, we looked at Kepler's third law, which says that the square of the planet's orbital period is proportional to the cube of the planet's average distance from the Sun, which is a complicated way of saying that bigger orbits take longer to complete than smaller orbits.